This is question 15 from the third CSAT sample paper. In this question, we're given this function, which is like a little box, and box of r is the greatest integer less than or equal to r. So for instance, if r is 1, this is going to be equal to 1. If r is 1.2, it's also going to be equal to 1. If r is 2.1, it's going to be 2, etc. So you can think of it as just the integer part of r. If the inside could get negative, you'd have to think slightly deeper, but it doesn't matter because the thing inside is always going to be positive. So also k is a positive integer, and we're asked to solve box of kx equals k plus 1 times box x, where x is greater than or equal to 0, and we're asked to consider the case k equals 2 first. So since they ask us to do that, we might as well. So if you want to have a go at the k equals 2 case, pause the video now. Okay, so I think a good way of understanding this is to look at the graph. So let's graph the two sides here. So I've drawn some axes, and these are the two functions I want. If k is 2, this is box kx, and then this is going to be 3 box x. Let's do this one first. So the thing to remember is between, say, 0 and 1, this is always going to be 0. Between 1 and 2, the inside is always going to be 1. It's central all the way up. So the value only changes when I go from one integer to another. So what happens between, so I'll just consider this each integer stretch at a time. What happens between 0 and 1? Well, box x is 0. So I'm just getting a line between 0 and 1. The only thing I have to worry about is the endpoint. So if x is 0, then the function is 0, that's fine. If x is 1, then box x jumps up to 1, so this jumps up to 3. So I have the line between 0 and 1, but I've drawn a closed circle at 0 and an empty circle at 1, because at 1 the value isn't 0, it's up here instead. So then between 1 and 2, what happens? Well, box x is just going to be 1, so we get 3, and we get a similar line to this, but at 3. And then if I continue, it's just going to jump up by 3 every integer, and it's always a closed circle at this end, open circle at this end. I haven't gone all the way up to 9 on the axes, because most stuff is going to be down here, but you can see I started the line that starts at coordinates 3, 9. And then what happens with this one? Well, the thing to notice here is the value of the inside doesn't change every integer, it changes every multiple of a half. Because if x is equal to a half, then the inside is equal to 1, and box of it is no longer equal to 0. So between 0 and a half, then this is between 0 and 1, so we get 0. I've drawn it underneath so as not to overlap, but it's at y equals 0. Again, closed circle, open circle. But at x equals a half, the value jumps up to 1, and it stays there until we get to 1. X equals 1, the value jumps up to 2, and it's going to stay there until we get to 3 halves, when it will jump up to 3. So you can see these are going to be half the length, but they're also moving up 1 each time. So we can see there's an overlap here between 0 and a half, and here between 3 halves and 2, but here they just miss each other because there's a closed circle for the green and an open, sorry, a closed circle for the blue and an open for the green. By the way, I've drawn the blue slightly underneath the green where they overlap, but they are at the same y value. And then if we imagine trying to get the blue function to overlap with this, well, the endpoint of this is going to be at 4, where this function takes the value 8, and that's below the value of this, which is 9, so they're not going to overlap here. You can see they're therefore going to miss at every subsequent time. And another way to see that is if we look at these closed circles, for the blue function, they all lie on the line y equals 2x. If x is a half, we have 1, 1, 2, 3 halves, 3, etc. all the way up. Whereas for the green, they lie on the line y equals 3x, so it's going up more steeply, and therefore once the blue and the green miss each other once, the green's always going up faster, so they're going to miss each other subsequent times. So what's our solution for this? Well, it's two ranges, this and this, and we can write them as 0 is less than or equal to x is less than a half. We have to be careful about the strictly less than here, because at half the value is this and they're not equal. and 3/2 is less than or equal to x is less than 2. Okay, so that's a graphical method, but it might be harder to generalize in terms of k, because for k, if this is kx, then the value of this is going to change every time we go past a multiple of 1 over k, so these blue things are going to get very short. And this is going to be k plus 1 times box x. That's still going to change every time we go past an integer, but it's going to jump up by a large amount if k is large. So it might be difficult to draw. I think an easier way is to now start thinking about it algebraically. Now we have this intuition. So where do these ranges come from? Why is it these two ranges? Well, we can think, if we want these two things to be equal, then what do we want box 2x to be, bearing in mind this is an integer? Well, it's got to be a multiple of 3. It was going to be equal to this, because this is 3 times an integer. So we can start off by thinking, well, 0 is the smallest multiple of 3 we can have, and that's going to happen if x is between 0 and 1. We could have 3 if x is between 1 and 2, or 6 if x is between 2 and 3, etc. But, well, I'll call these a, b, and c so I can refer back to them in a second, so you can consider the range on x for each of these. But it's worth noting that these two work and this one doesn't, and then we know every subsequent one doesn't. And why is that? Well, we think about what x is constrained to be from here, because when we have box of something equals something, that means x has to lie in a particular range, so the inside is between two particular integers. So we'll go through what box 2x has to be for this to be equal to 0, 3, or 6. And these inequalities are just what 3 box x has to be at each of those values. So if box 2x is equal to 0, then we need 2x to be between 0 and 1, or x between 0 and a half. And, okay, this is a case where there's an overlap. If box 2x is equal to 3, then we need 2x to be between 3 and 4, so x is between 3/2 and 2. That's okay because there's an overlap between this inequality and this inequality, or this range and this range, because this starts at 3/2 and this ends at 2. If we go to the next one, if box 2x is equal to 6, then 2x needs to be between 6 and 7, so x needs to be between 3 and 7/2. And we also have this inequality for 3 box x to equal these things. But now there's no overlap between these ranges, because this starts at 3 and this ends at 3, but it's a strict inequality. So there's no overlap. And what we can see is that's going to continue, because here the left-hand side of each range is increasing by 3/2 each time, but here it's just increasing by 1. So, for instance, the next, and so is the endpoint. So the endpoint in the next range is going to be 4. Here it's going to start at 4.5, and therefore there's not going to be any overlap, and that's going to continue. So we know only these two ranges work. So now let's try to apply that to the case where we've got k instead of just 2. Okay, so now instead of having box 2x, I've got box kx, and instead of wanting this to be equal to a multiple of 3, it's got to be equal to a multiple of k plus 1, because it's equal to k plus 1 times box x, which is a whole number. So what are the multiples we could have? Well, again, we could start at 0, and that's going to apply for x between 0 and 1, because then box x is 0, and k plus 1 times box x is 0. And the next integer we could have is, the next multiple of k plus 1 is just k plus 1, and that means we need box x is 1, so it's between 1 and 2. Next multiple we could have is 2k plus 1, and then we need x between 2 and 3, etc. And from the case k equals 2, we saw that eventually this breaks. So that makes sense, because if we think of k plus 1 times box x as something that looks a bit like a straight line, so remember we said that 3 box x looks like it's the line y equals 3x, except kind of turned into steps. Well, this is going to have a gradient basically like k plus 1, if we think of it that way, and it's going to have a gradient of k, so this is eventually going to overtake this. So it should only work up to some number n. We have to work out what n is. So let's just label these cases by the multiple of k plus 1, so 0, 1, 2, up to n. And we'll think about what range x has to be from here, and then we'll look for where there's an overlap, the same way as we did for k equals 2. So if the multiple is 0, then that means that x has to be between 0 and 1 over k. Why is that? Well, we need kx to be between 0 and 1, and therefore x is between 0 and 1 over k. And we still need this inequality. If the multiple is 1 times k plus 1, then kx needs to be between k plus 1 and k plus 2, and x needs to be between those things divided by k. So 1 plus 1 over k, and 1 plus 2 over k. And we also need this inequality to be true. So in general that's fine, because look, this starts at 1, goes up to 2, and this starts at something bigger than 1 and goes up to something that, unless k is too small, will be less than 2. So there's going to be an overlap. And so I'm imagining here k is quite big, so we can do lots of these cases. So a similar thing for if the multiple is 2, if we're looking for this to be equal to 2 times k plus 1, then the inside has to be equal to 2k plus 2, and therefore it has to be between 2k plus 2 and 2k plus 3. So Oxbridge is equal to 2k plus 2. And therefore x has to be between those two things divided by k, so 2 plus 2 over k and 2 plus 3 over k. And this is going to carry on all the way down until we get to n. And you can see each of these things is basically something times 1 plus 1 over k, and then the right hand side of the range is the same thing plus an extra 1 over k. So here it's going to be m plus n over k, and here just n plus 1 over k. And each time this inequality is x between n and n plus 1. And we want there to be an overlap between these, but we're imagining n is the last number for which there's an overlap. So we need to check what needs to happen for there to be an overlap. Well, if we observe, the left-hand side of each of these is increasing by 1 plus 1 over k each time, and here the numbers are just increasing by 1 each time. So these are increasing faster. So eventually this will be too big. What happens if it's too big? Well, it means there's no overlap, because this has to be bigger than this, and therefore x can't satisfy both of these at the same time. So that means we need this, the left-hand side, to be smaller than this in order for there to be an overlap. So we need m plus n over k to be less than n plus 1. And we can cancel n, so we just get n over k is less than 1, or n is less than k. So this works for n less than k. We want n to be the largest integer for which it works. That's going to be k minus 1. So that means we get one range for each of these values up until k minus 1. It's worth just checking what happens if n equals k plus 1. Well, this is going to be k minus 1. This is going to be 1 minus 1 over k. So that simplifies to k minus 1 over k, and on this side it's going to be the same plus an extra 1 over k. So it just equals k. And there will be an overlap, because this will go from k minus 1 to k, and there are values of x this allows that are less than k, and likewise here, so there will be an overlap. So from that we just need to write down the solution, where the solution is all these ranges, because each of these is inside the corresponding range here. So the overlap is just each of these ranges up until n equals k minus 1. So I'll write them all in terms of n, where now n just means the multiple here rather than the final value of n. So they're all of the form n plus n over k is less than or equal to x is less than n plus 1 over k, where n starts at 0, can be equal to 0, and goes up to k minus 1, and it can be equal to k minus 1.